So here we see our very first problem that includes a spring in a cable structure. And it is my experience that students first fear springs and they don't know how to calculate it. But as I will show you now in this application of this problem, springs are actually just an addition to what you know already. So nothing changes. You don't have to change your approach. You don't have to learn something new, except you have to add at the end what we just talked about, and that is the spring constant. And I will explain that as we move through the problem. But what we have here is a lamp of 5 kilograms that is hanging downwards, and there's one sloped member or one sloped cable and one horizontal. Think of it as a cable, but it's of course a spring. And we have node A, B, and C. And to solve this problem, just like before, we need to first release node A, because we have one known force, which is the 5 kilogram, and then we have the unknown force in cable AC and the unknown force in spring AB. And let's recall that we can really cut the system however we want to. So for example, I could release the system like this if I want to release node A, but I could also, for example, release the system like this. It does not really matter, right? So I will now draw the free body diagram for the system. I usually prefer this one, the inner one, the smaller one, but it doesn't really matter. So let's go ahead and do that. Let me pull out my ruler here and copy the 30-degree line. So first I start with my free body diagram, and my free body diagram has a cable that is sloped. It has a horizontal cable and a vertical cable. And of course I need a coordinate system. So in this case, I'm actually going to place it at the center just to do it a little bit different like I did before, just so you see that there's a variety of ways of doing this. So there's X, Y. And now I need to include the information that I have. First of all, I know that there's 5 kilograms hanging here, and 5 kilograms, because we're using 10 meter per second square for gravity, really relates to 50 newtons. So we're going to use 50 newton to solve this problem. And by the way, sometimes I see students solving forces in cable structures in terms of kilograms, but that is not a force. Kilogram is a unit of mass, and if you want to solve for a force, it has to be in force units. So please keep that in mind. Now, let's move on to our unknowns. So I first have an unknown here, which is called FAB, and I have a second unknown, FAC. And understand, please, that FAB is really the force that's acting on the spring, but notice that I did this cut here, and so therefore I don't have to worry about the fact that there's actually a spring here. Even if I cut here, I don't have to really include it because the spring is not really cut. So we will only worry about the spring at the very end. All right, of course, I need my components. There's only one sloped member here, so only that has actually components. So let's add those. And I, of course, need also directions and names for those. Remember all the rules that we have. So FACX and FACY. Last but not least, I need my angle, which is right here. Let's call that alpha, or actually that's 30 degrees. And now I can start solving. In fact, I'm going to take a very shortcut now because you're already so familiar with solving these problems thanks to all the homework that you are allowed to do in this class. So only this force can really balance this force. There is nothing in FAB that really can hold the lamp up. So the only thing that holds the lamp up is FACY. So without writing down a real equation, I already know that that is 50 newtons, right? So for your educational experience, of course, I'm going to say that you would write sum of the forces in the y direction is equal to 0, upwards positive, and then you would state that 0 is equal to plus FACY minus 5 Newton. And again, if I were in an exam, unless I'm specifically asked to write down this equation, and most often you will be asked, but if I'm not in an exam, I would have just stated that FACY is equal to 50 Newton. Let's fix that. So 50 Newton. Now, if I know that, I know everything else already, right? So now that I know this one, I can, of course, use my 30 degrees to find the hypotenuse. I can find the horizontal, and once I know that, I can actually find FAB. So let's go through that. So FACY is nothing else than FAC multiplied by the sine of 30 degrees. So therefore, FAC is equal to FACY divided by sine 30. But keep in mind that sine 30 is nothing else than 0.5, and so therefore your FAC would be equal to 50 Newton divided by 0.5, which is nothing else than 100 Newton. And that does not get any easier. This is not a result in this case because the problem doesn't ask for that. If the problem was asking for the solution to all the cables, I would double underline this right now, but here we're only asked for the stretch. So to get the stretch, I really need to understand how much force is acting in this cable here, FAB. We have calculated FAC, so that's the force in this diagonal component. And what I need now is the horizontal component so that I can balance that in the x direction. So let's write down that. So if I want to find my FACX, then I really need to say that FAC times cosine 30 is that component. And so that relates to 100 Newton multiplied by cosine 30. And that is nothing else than 86.6 Newton. And so now what I know is that 86.6 newtons is actually acting in the horizontal direction here at AC. And that has to balance FAB, which now, of course, as an engineer in the real world, I would have already answered this, but for the educational experience, I would write the sum of the forces in the x direction is equal to 0, positive to the right, and 0 is really equal to minus FACX plus FAB, and that would be equal to minus 86.6 Newton plus FAB, and therefore we know that FAB is really equal to 86.6 Newton. And notice that this is technically plus, and that means that the cable is in tension, right? So understand, please, that we assumed every force to pull away from this node. Remember that this is node A, right? Let me highlight that. So this is node A, and that node A, we assumed every force pulling away from it. And if they come out to be positive, that means that we have tension. That is kind of the definition of tension here, because we're pulling away from the node. All right, but we are asked to find the stretch in the spring. And the stretch in the spring now, we can actually draw a second free body diagram for that. So to be complete here, so let's say for node A, I'm now going to draw a free body diagram for the spring. So free body diagram for spring. And that is as simple free body diagram as it ever will get. So I release the spring, and I just have a force here and a force here. And notice that I need forces on both sides. So I release the spring. So really what I did here, let me go back and let me show that to you, is I cut the system like this. And only if I have arrow to the left and to the right, this can be in equilibrium. But now I have to say that the force that keeps it in equilibrium is FAB, which is equal to 86.6 Newton. And that is literally everything I need. And my spring constant equation, of course. Remember that F is equal to K times S. And so my S is equal to F over K. And applied to this problem, what that means is that the stretch in the spring is equal to the force 86.6 Newton divided by, what was our spring constant? 300 Newton. So 300 Newton per meter, actually. And if I calculate that out, what I will find is that the stretch in the spring is really 0.2857. 0.2857 meters. And this now is a real result, because that is what the problem asks of us. And so I need my answer arrow. And I now solved the spring constant problem, which hopefully learning by doing here applies. And we can now see that we only needed to worry about the spring constant once we found the force in the spring, right? So please understand that here, this cut down for the spring that I just added is equivalent to the cut up here. And so that cut is in balance. So whatever happens here to the right has to happen here to the left. So this here is actually also FAB. Maybe I should add that as well. So FAB. And once I knew the force in that spring, I just applied it to the spring and then I calculated the stretch in the system. And it's literally as simple as that. So really what you need to learn is how to find equilibrium at nodes. So let's make that a little bit more complicated and take a look at more advanced examples. All right, our problems become a little bit more interesting now. We are now looking at a problem where we have a box hanging on two cables that are both under an angle. In fact, they are described by their relations here, 3, 4, 5 for this one. And this here is 3, 3, and then of course square root of 3 squared plus 3 squared. But we have a box here and we assume that the dimensions that we see here are the unstretched, unloaded system. And that the box here really can only move downwards in a perfectly straight line. This may not be true in real life because the length here is different than here and maybe the stiffness is different here. So the stiffness, by stiffness I mean the spring constant. Therefore, it may shift a little bit to the left and to the right, but that is irrelevant to us here. We move downwards in a perfectly straight line. And then we also assume that the box has a volume of 8 liters. And of course, let's write that down right away. So 8 liters of water is nothing else than 8 kilograms. And that means it's 80 Newton, right? So we have 80 newtons acting here. And now we can calculate the stretch in cable AB and AC. So AB is here and AC is here under the assumption that the box is completely filled with water. So that I already did here. The strategy to success is always a free body diagram first. And let's talk about an important aspect of free body diagrams for released systems. So I just released this system here. And what did I do? I really cut through 1, 2, and 3 parts of the structure. But in reality, I only cut through 2 unknowns. So this is not known and this is not known. This is effectively known because I have this value available here to me. Please understand that the only reason I will be able to solve this is because I have only 2 unknowns. And why is that important to understand? Because we have the sum of the forces in x is equal to 0, and we have the sum of the forces in y is equal to 0. And that means I have 2 equilibrium conditions. And therefore, I can only solve 2 unknowns at a time, because if I have 2 equations, I cannot solve more than 2 unknowns. Or likewise, if I had 3 unknowns, I could not solve that with two conditions. And that is why when you draw free body diagrams and when you cut the system, you always have to make sure that you only cut through two unknowns. In other words, if there was another spring or another cable, let's say here, let's say I have another spring here, then this would not work because I also cut the spring here and I would end up with 1, 2, 3 unknowns, and therefore my two conditions would not be enough anymore. And you could say, what is with the sum of the forces in the z direction? Then I have a third condition. And I would say, yeah, that is true if you have the sum of the forces in the z direction, but it doesn't help you because this system only exists in xy. So this would not be solvable with the methods that we have in this class. Therefore, let's remove what I just drew here and let's fix our structure and understand that we can only solve this because we are cutting through two unknowns here. All right, let's draw the free body diagram for node A. So free body diagram for node A. And I'm going to copy my slopes here. So the first one is a 3, 4, 5 triangle, and then we have the, sorry, that's actually a 3, 3, so that's a 45 degree. And then here we have a 3, 4, 5 triangle. And I believe we said that we have 80 Newton acting on the system. Now my unknown here would be FAB. And I have an unknown here, which is FAC. And I need components. So let's add those components. And vertical components. So FAB, Y, FABX, FACX, and FACY. Now I can either use angles or relationships. So let me actually use relationships for the right side because I know that is 3, 4, 5, right? So I have 3, 4, and 5 here. But then on the other side, let's just make our life easy and let's say that I use 45 degrees. So 45 degrees. I could have, of course, also calculated the length of the diagonal, but that doesn't matter here in this case, which route I'm going down. So now we can solve this, and it's a little bit more complicated than before when we talked about the lamp. Remember, the lamp, we only had on the left side a sloped member, whereas the right side didn't have one. So now, in this case, because both sides are sloped, that means that the vertical force is shared between FBY and FACY. So that equation would read plus FABY plus FACY minus 80. Whereas the x direction is similar to what we've seen before. But in this case, let's write down the x direction first. So the sum of the forces in x is equal to 0, positive to the right. And 0 is equal to plus FABX minus FACX. And similarly, in the y direction, I have 0 being equal to plus FABY plus FACY minus 80 Newton. And once again, this is very similar to what we talked about before. I cannot solve this equation set as it is right now because I have 4 unknowns. FABX is different from FABY. But I can express, of course, FABX in terms of FAB. And I can express FABY also in terms of FAB. So let's go ahead and do that. So plus FAB, and now divide it by 5 and multiply it by, this is the x direction, so 4. So 4 over 5 minus FAC times the cosine of 45. Or actually the square root of 2, right? It's a 45-degree angle, so you could also divide it by the square root of 2, but let's not do that. Let's use the sine and cosine. So multiplied by, this is the x direction, so I prefer to use cosine. Of course, it's the same for 45 degrees angles, but that doesn't make a difference. I want to stay consistent. In the y direction, now we have FAB multiplied by 3 over 5 plus FAC times the sine of 45 minus 80 Newton. And that now can be solved because now we have two equations, 1 and 2, with two unknowns. In fact, for educational purposes, let's highlight them. So these are identical to one another, and now we can highlight them, or we can memorize that this is equation 1 and this is equation 2, which now I can solve by substitution methods, which I don't believe I have to show you once again. I will just give you the results. I will tell you that FAB in this case comes out to be 57.14 Newton. And FAC really turns out to be 64.65. Once again, these are not results, although it seems that way. But what we're really asked for here is the spring stretch. So let's calculate the stretch in the springs, which FAB, the force that sits in the spring FAB. And that had a spring constant of 300 newtons. So remember once again that S is equal to F over K. And so if I do the stretch in spring, what is it called? AB. In AB, then I would take the force FAB, so that was 57.14 Newton, divided by 300 Newton per meter. And I would find that that is equal to 0.190 meters, really. That is actually a result, so therefore I'm double underlining it. And not just double underline it, I also give it an answer error. So now that is taken care of, but I have to do the same thing for SAC, which is the other force now, which is 64.65 Newton. But be careful now, it's a different spring constant. So let's zoom out and let's take a look at the entire picture here. So that needs to be divided by 200 newtons per meter. And if I type that into my calculator, I will actually find that it's 0.323 meters. And that again deserves a result, double underline, and an answer error, because that is really what was asked of us here. And that concludes our problem. We now found the stretch in the springs by applying the stretch formula, or really Hooke's law here, to the results from our free body diagram and our equilibrium. So we did not get confused by these springs here initially. In fact, we ignored them here. If you take a look at these equations and this free body diagram, we completely ignored the fact that there were springs, and we just then later on said that, hey, AB is actually connected to a spring, and so is AC, which is connected to another spring, and we were able to use that information to find the stretch in each springs. If these stretch are really practical is a different question. This is obviously very large, so 0.3 meters, that's 32 centimeters, that's almost like a foot. And if that would move a foot, that is probably not something practical in structural engineering, but it gets the educational point across. But I believe that completes our problem here, and we are now well prepared to move on and to solve any homework problem that includes springs.